Since photolithography is the key for IC fabrication, allow me spend some more time for a little bit detailed explanation. What is photolithography? This is the whole process for photolithography. Never mind what kind of layer you would like to fabricate. So this is some kind of three-dimensional view, and I help you to cut. Then see the vertical cross-sectional view. Alright? Here is the cross-sectional view for the wafer. Alright. So from the very beginning, on top of the wafer, we need to have a layer of photoresist. Yeah, never mind how you spread the photoresist over the surface of the wafer, you need to spin it. Okay? To make, hopefully, the photoresist uniform distribute over the wafer surface. You need to pay attention to that. We only fabricate or diffuse any kind of layer on the top or inside the wafer. Everything is around the top surface of the wafer or your chips. Alright? What's to the bottom? Nothing. This is usually called the substrate. That's it. So everything is on the top or around the surface, the top surface of the wafer of the chips. Okay, so after you uniformly distribute the photoresist over the wafer top surface, then above it you can have the mask. And what is the mask? Actually, it needs to have 100% what you would like to have for each layer. Okay? You need to draw it before fabrication, layer by layer. And how about fabrication? Also, it can only be fabricated layer by layer, especially from the bottom to the top. Just like how you construct the whole building, right? You don't have any way to construct the top floor, then downward to the basement. No. Everything needs to be constructed from the basement, floor 1, 2, 3 to the top floor. That's it. No more. Alright? That's it. But for IC fabrication, that is in theory. For gate, polygate, usually the order for fabrication needs to be reversed. Later I will explain. Anyway, let's go further. For each layer above the photoresist, you need to have the mask. It contains all the patterns you would like to have, you would like to fabricate for such kind of layer. Then above it, above the mask, you need to expose all of them to, in the past, UV light, 紫外线. Right now, EUV light. And what's the difference? Later I will explain. Oh, I put everything for later explanation. No. Step by step. So after exposure to the UV or EVU light, the portion exposed will be changed in chemical property. 它的化学特性曝光之后就会改变。Then you can use another chemical solution to wash out the exposed one or unexposed one. It depends on the so-called positive photoresist or negative photoresist. For positive one, the exposed area will be washed out. For negative one, the unexposed one will be washed out. That's it. So you can see after exposure, the chemical property here will be changed, right? Then you can wash it out also. That is for positive one, right? For negative photoresist, you wash out the unexposed one first. So, after you wash out the exposed one, for what? Maybe to fabricate some layer here, or to diffuse, to imprint some kind of impurity inside the surface. Okay? That's it. No secret. That's it. Alright. So you can see that is our dream in the past. The feature size scaled down all the way from microns right now to nanometer. As I mentioned in the past, we learned 2 micron instead of 2 nano. No, 2 microns from RCA till now. I think TSMC already develops the process for 2 nanometer. Okay? It's already on schedule. Yeah, anyway. For how many years? I guess more than 4 or 5 decades. Okay? We made it. Taiwanese make it for almost 3 order improvement for the size. 3 order means what? How about the area? By 2, right? So totally, you can see for 4 to 5 decades, we scale it down for 1 million times. That is till now on Earth the best development, the best progress we can make for the whole industry, never mind in what field. It's really amazing. We can scale down the device size by 1 million times, only within maybe 40 to 50 years. It's really, truly amazing. And it changed our face of life very, very much. Okay? Without such kind of technology development, you don't have the chance to enjoy the smartphones. Everything will become stupid. Never mention about your cars, just like my own. It is not some kind of autonomous cars, but yeah, semi-auto drive. So for myself, especially on the highway, I only need to set how fast it could be. Then the radar or the LiDAR can help. Only radar instead of LiDAR. For truly automatic one, you need the help from LiDAR with laser. Okay, but for semi one, yeah, radar will be good enough. Okay, it can help me to trace the car in front of me, to speed up or to slow down all the way to the speed I set. And also it can help me to steer my wheel to control the direction of the car. For the real automatic one, you can set the destination then, yeah, fall in sleep. That is our future. In the near future, we will make it. Actually, we make it already now, but for safety concern, we still need to be curious. But if something going wrong, then whom will be blamed? Yourself? I mean the drivers? Or the car companies? Who knows? Yeah, maybe the car company will put the blame on AI software. Anyway, let's wait and see. It will come true very, very soon. But it needs the help very much from semiconductor industry, because to implement it, how about the software? You need software, but how to run the software? You need chips. Okay? So this is the reason why Taiwan is much more important than before. Not only China would like to take over it, to the other foreign countries, just like America, Japan, or European countries, they also show much interest on us. So please, after graduation, work for the industry to make a big money and also to help us defend Taiwan. Okay, it is scaled down all the way. Anyway, into the future. Maybe the limit will stop around 1 nanometer to my memory and no more. Unless you change the material for silicon. Sorry for that. We will stop at the node called 1 nanometer. And beyond that, who knows? Maybe we need new material just like nano carbon tube. 纳米微碳管. Okay? Or the other way out, that is the more likely solution, is to pile up. We still scale down all the way from micrometers all the way to 1 nanometer and then no more. So, how can we integrate more function, more devices on the same chip? We need to pile it up 3-dimensionally, vertically. Okay. Luckily enough, TSMC is already the best on earth for 3D packaging and testing. That is the way to defeat Samsung. Samsung, from the beginning, was the best on earth for 3D chips. But right now, TSMC is the best. Much, much better than Samsung. Okay? The other issue is CD. What is CD? Not DVD. Okay? It is called critical dimension or feature size. Okay? The feature. Anyway. So this is what I would like to tell you why. Right now, we don't depend on lambda rule very much because this is for 90 nanometer technology. But the actual size at the fabrication is only 59. It is good, but it is hard to define everything with lambda, right? So lambda means what? By definition, 90 divided by 2. But right now, it becomes 59. Actually, is in actual size. So, again, on the top of silicon, you added some materials with the help of photolithography, remove the part you don't need, blah, 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 all the way, layer by layer. Okay? Many of the materials, just like polysilicon, metal, silicon dioxide, and how to fabricate such kind of layers with deposition, sputtering, right? Oxidation, diffusion, blah, 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 and many of them. Okay, from the very beginning, we need to do such kind of oxidation. To make silicon dioxide the key ingredient. But how to make it? For example, we have such kind of crystal oven, 石英炉管, okay, coarse tube. So you put many of the wafers inside the tube with very high temperature, very high oxygen density to make such kind of oxidation for silicon. So if you go outside to pick one rock, then watch it for oxidation. Oh, how long you need to take? Thousands of years. Okay? We don't have such kind of American time for waiting. We need to speed up such kind of oxidation. But how? High temperature and high density. That's it. Okay. So we oxidize many wafers at the same time inside the tube. Here is for oxygen to get in, there to get out. And you can guess the density from here to there will be reduced. Why? Because the oxygen will have chemical reaction with your silicon wafers, right? After such kind of oxidation, and gone, it becomes silicon dioxide. So, again, the density of the oxygen will be reduced from the input to the output. Not only that, but also Among the wafers, you can see, the wafer look like this. How about the middle? How to do such kind of oxidation? Where to get oxygen for oxidation? Oxygen needs to diffuse from the boundary to the middle. From the boundary to the middle, right? So what you can guess? The oxygen density is higher at the boundary, is lower in the middle, right? So in practice, never mind how long you waited, you wait for oxidation. Never mind how high temperature, how high density, how long. The final shape for the wafer, for the dish, will like this. Okay? To both ends, according to more oxygen density, it will be thicker. In the middle, it will be thinner. Alright. This is something, again, we call it mismatch, but more systematic mismatch, because it happens in the system way. Okay? It is some kind of destiny. 这是命运. If your location is here, then you get thinner oxidation. If you are there, you get thicker, right? So how about the performance of your MOSFET? If you have a MOS here and other MOS there, I promise you, the conductivity here is much better than there. That is the so-called systematic mismatch. So, for your layout, if you would like to match two of them, many of them, please, according to such kind of systematic mismatch, they had better be laid out close to each other, two of them. Okay? As close to each other as will be better. If you have such kind of stupid layout, one here and two there, oh, sorry for that. You need to face a lot of systematic mismatch. Their performance will be really poor after fabrication. Okay? So, for systematic mismatch, usually for matching, we need to have common centroid layout, just like what I say, 1, 2, 2, 1, 2, 1, 1, 2. That is for second order. If that is not good enough, then 1, 2, 2, 2, 1, 1, 2. Then 1, 2, 2, 1. This is for third order, blah, blah, blah. I will have detailed explanation for this. Maybe in chapter 5 or chapter 6. Okay, I will do my very best. Okay. Why? I am different because I will teach you why and then how. Most of the professors on earth will teach you how, but they don't teach you why. Okay? And it is really important for students or new engineers to know why means you may possibly survive in the future when you face the new challenge, the new mismatch. But if you only know how to do it, then no way you can survive. You don't know the causes for such kind of mismatch. How can you deal with them? No way, right? So I'm really proud of that. I will teach you everything I know from the beginning, why it happens, and then how to deal with it. Okay? And this is a very good example for systematic mismatch explanation. It happens all the same. The oxidation thickness from here to there, from the input to the output, from thicker to thinner. Okay? And then, that is among, it is also a very good to tell you, that is the so-called wafer to wafer mismatch. Okay? Even on the same wafer, I told you, it looks like that. On the same wafer, we have what? Die to die mismatch. the same time, we have device to device. Okay? But, so, wafer to wafer mismatch, larger than die to die, larger than on the same time, device to device. Even worse than wafer to wafer is what? Lot to lot. For Apple chips, right? From the beginning, maybe it would only like to get 10 millions. But after very good sale for the newest iPhones, it tries to get more and more. Okay? So, you don't expect all the chips for the same iPhone fabricated at the same time. No, sorry for that. Alright? Maybe in this month, they still think it's not good enough. Then they put more order, but not for tomorrow, right? No. Everybody compete for the resource, for the fabrication resource from TSMC. Even for Apple, I think maybe it needs to wait maybe 1 month, 2 months, or 3 months. Okay? For next lot, CIT. Okay, so with this very good example, I not only show you why we have systematic mismatch, but also I tell you why the lot to lot mismatch will be larger than wafer to wafer, then die to die, then on die mismatch, blah blah blah. But why lot to lot? Because if it is fabricated right now, the temperature is low, right? The air pollution is high. A few months later, the temperature become higher and the air quality becomes better. Fewer dust you can expect inside TSMC clean room, right? So nothing will be the same. Even for the same company, even for the same chip, fabricated in different time, you need to face different challenge, different mismatch. Okay, that's it. Then, for the lithography, as I explained already, no more for that. Then, for the open area, as I mentioned, after photolithography, some of the area will be opened, right? Exposed or unexposed to the UV or EV light. After that, if you would like to make it become P-type, N-type, you need to do doping. 2 ways for doping. In the past, diffusion. Oh, even right now, I think we have diffusion, especially for lightly doping, just like N-well, deep N-well, blah blah blah. Okay. So for diffusion, how to make such kind of diffusion happens? You need to vaporize the impurities to be diffused. For P-type, we have arsenic, boron, okay? Or phosphorus, blah 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 for N-type. Anyway, anyhow. Okay, so this is a very good explanation. To vaporize the impurity. What kind of impurity? Yeah, they are all solid. 会当点扣扣的物件，如何变成蒸汽？哦 we need very high temperature, right? And not only very high temperature, but very high pressure. For what? To speed up the molecules, the atoms. Then the atoms with high enough speed to collide with your monosilicon. We only have from the beginning monosilicon. Later I will show you how to get polysilicon. Okay, from the beginning, the wafer, according to the help of seed, we have single crystalline, monocrystallization. Okay? So everybody has the same atoms. And the fast enough atoms will collide with the atoms in the crystalline. Then kick out some of them and then take their position. That's it. That is the meaning for doping or diffusion. Okay? You need to kick out somebody, then replace it. also need to be very, very careful. For example, if you have such kind of boron for p doping, right? Then, maybe it is incorrect. P should be for phosphorus, so B should be for boron. Anyway, as I mentioned, we have silicon here, silicon there, right? If the boron atom gets high enough speed to kick out this silicon and take its position, congratulations, we doped somebody there. But to keep the same crystalline, be careful. The impurity cannot get bonded with the same atoms. Okay? If you have such kind of boron to boron, then the bond here will have different physical structure. Then it is no good. Just like polysilicon I explained already, you have some kind of cracks here because its structure is totally different from silicon one. Okay? It is no good for current conduction. So, never mind how much for doping, the density. Please don't get such kind of impurity to impurity bonding. Okay, but how to make sure you don't have such kind of impurity to impurity bonding? The doping needs to be very, very light compared to monosilicon. So usually, how to measure such kind of doping? In ppm. Okay, ppm means what? See? 1 out of million. You cannot find your own neighbors. No. You will be surrounded by all silicon atoms to make sure no boron to boron, phosphorus to phosphorus bonding. Okay? Again, to make sure what? There's exactly the same crystalline structure before or after doping. Okay, but we have plus doping, high doping, and low doping, right? A few ppm to maybe hundreds of ppm, blah, blah, blah. If you are interested, please go back to reread your microelectronics. 1 ppm doping will enhance silicon conductivity by almost 1 million. Okay, it's really amazing. -6 order of doping can enhance the conductivity by 6 orders. It's really, really amazing. Okay? That is the secret. That is the magic we play with doping. Without doping, pure semiconductor usually means useless. Okay? Anyway, not only diffusion, but also implantation. Because, I forgot to mention another very important phenomenon here. For diffusion, you have no way to control the direction of your atoms. Okay? They try to fly by themselves. So they will diffuse in this direction, diffuse in that direction. Wow! No way to focus the direction. So what will happen? You have a short open here, a small open here, right? According to the random direction for diffusion, what you get won't be what you see. What you see won't be exactly the same as what you get. Okay? I'm really sorry for that. So maybe from the beginning, you have this opening for your P plus region. But after fabrication, especially after diffusion, the real area will look like that. I cut it and have the cross-sectional view here for you, right? The atoms don't diffuse in this direction only. No, in that direction. So you have this one, that one, here, 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 and there. We call it side diffusion. Keep this in mind, side diffusion. So the area after diffusion will be larger than your imagination during layout. Okay? To control such kind of doping more accurately, actually, more than often, such kind of side effect, side diffusion is harmful for your performance, right? How to control it as good as possible? You need to change the way of doping. So, humankind created implantation, 布置. Okay? For implantation, oh, sorry. Yeah, it means what? We use ions. Here. Right? We call it ion implantation. We use ions. Ions means what? They are not atoms. They are charged atoms. To be charged to be positive or negative. But with charges, all those atoms can be focused, then accelerated. Right? Two major purposes to make the atoms become ions. One is to focus all of them for doping. In theory, with the same direction. Bingo. The second is to speed them up, to easily kick out the silicon, then take their places. Okay? So, by ion implantation, according to focusing, you can see what you get will be much closer to what you see during layout. I mean, compared to diffusion. Are you happy? But I still need to warn you. Even after focusing, you cannot expect all the ions will hit lattice in the same direction. Exactly. No. Some of them still be defocused, but much better than this one. Okay? So, don't expect you don't have such kind of side diffusion. No, you had some of them, but much better than this. Okay? The other lesson you need to know, we still call it side diffusion. Why we call it side implantation? Don't ask me. I'm not such kind of material guy. Okay? According to naming, even with implantation, we still call it side diffusion. Right? So, what is the major difference? Again, that is what you plot. Okay? During layout, with diffusion, you may have this. Much wider area for side diffusion. But with implantation, it is much smaller for such kind of side diffusion or side implantation. Okay? Then, this is even better explanation for such kind of ion implantation. So from the beginning, we have such kind of ion source to charge the atoms to be positive or negative. Then you can use the magnetic field to turn their way, right? To focus them, to speed up all of them. Then this is for speeding up, right? Acceleration tube. You can see if it is negative, free electrons, then you have positive here, negative there, right? They will be sped up. And then we have, just like CRT, okay, we have a vertical parallel plate and horizontal parallel plate. This is vertical, that's horizontal angle. So you can see, for example, here, if you have positive here, negative there, then the free electrons will what? Will be redirect according to the parallel plate. Okay? The same thing is you have top and side. Alright? For the top one, if this is the your chip or your wafer, I don't care. Yeah. For the top ones, top to bottom one, you will control from here to there. And how about the sidewise? To scan from the left to the right. That's it. 1, and then 2, and then 3. So you make 1, then 2, then 3. I have no idea. But that is so-called scanning. 扫描. Okay? So in this way, don't expect all the devices on the same wafer will be fabricated at the same time. No. Sequentially. But in the very first, okay. We don't want to wait for a long time. The longer time you wait, the more systematic mismatch you need to face. That's it. Okay. The other one for implantation, not for diffusion, for implantation. Now, if you have a look at the wafer with the correct direction, if you look down the wafer, you will see this is some kind of structure for silicon. Okay? So, what is the impact? If you look vertically down on the surface of the wafer, you inject your ions directly perpendicularly into the structure. What is the consequence? It will penetrate from the top surface to bottom surface. You can see, this is some kind of big hole, very deep hole. Okay? So, perpendicularly implant your ions on the silicon wafer. It doesn't make any sense. Just like this. This is a wafer surface. Okay? Perpendicular implantation doesn't make any sense. Because it is hard for your ions to hit any of the atoms. It just penetrates from the top to the bottom. That's it. Say goodbye. Alright. What you can do? You can tilt your wafer. Okay? Or you can, how can I say, tilt your E-beam. 电子束, electronic bit. So anyway, effectively, the direction for implantation don't be perpendicular to the surface. You will be also tilted. 稍微偏一下. Then you have plenty of opportunities to kick this or that, right? You have plenty of opportunities to collide with the atoms, then take their positions. Got it? So, for implantation, it is not for diffusion. In the past, we don't have such kind of problem. But for ion implantation, the wafer needs to be tilted a little bit. Got it? So, this is what I would like to explain. Why? See? Perpendicular implantation. The doping concentration will become such bad. Okay? It will go deeper and the concentration is no good. On the contrary, if you tilt your wafer a little bit, 7 degrees, but TSMC guys told me 10 or maybe more than 20 years ago, for some process, they even tilt the wafer for 30 degrees. Okay. Anyway, it looks like that. For what? The concentration will look like this. That is what we need. Okay? To get the area as shallow as possible. Because if you make it just like this, for what? you will get more parasitic. For example, P substrate, N well. You can see P and N junction has what? A lot of capacitance, parasitic capacitance. Okay, so for such kind of implantation or doping, sorry for that, you will get a lot of parasitic capacitance. It is no good for your high-speed operation. Okay, and then the second issue is compare this to that. The concentration is really low around the surface. The concentration here, only a little bit below the surface, you get very high concentration. It is really good. Why? I mentioned already, all the currents, all the operation will be around the surface of your wafer, of your chip. Okay? So, the concentration becomes very high close to the surface, will enhance the current conductivity. Got it? That's it. So, again, how to make such kind of diffusion as shallow, 越浅越好, as shallow as possible, as higher concentration as possible, because you can reduce you can not only reduce the parasitic, but also enhance the conductivity. Why not? Alright? I'm talking about the source and drain region. Not only this, but also maybe the well, and well, P well, I don't care. Okay? That's it. The current, according to such kind of three-dimensional view of the device, the current will flow, this is, for example, this is, MOS. Okay, so the current will flow from here. You have contact, metal 1. Okay, so the current will flow from drain, then inside the drain region, right? Then penetrate through channel to source, then to the other side. That's for your any kind of, for example, this is the MOS. Okay, this MOS is here, right? The current flows from drain to source. But what is inside the drain and source? Actually, free electrons. The most, because they are major, they are majority carriers. 它们是主要载子. Okay, so it means what? The free electrons will go in this direction, then beneath the surface, all the way from source to drain, then to metal 1. Okay? So, the higher concentration here, the better conductivity for your free electrons. Again, keep this in mind. All the operations is around the surface of your wafer or your chip. The higher concentration, the better conductivity. But what goes wrong with such kind of tilt wafer? It means since after you tilt your wafer, for example, the implantation in this direction, right? It means what? You have more side diffusion here than there, right? Because you have some kind of thickness for your silicon dioxide, for your gate. If you implant in this direction, this area will be shaded by those two layers. 它们会被遮蔽，所以这边侧效应比较少，另外一边比较大。That's it. That's the secret. Okay. Maybe right. I'm an IC designer. Who cares? You need to care, especially for analog IC designer, because for your simulations, I don't care pre-sim or post-sim. Sorry for that. You have one assumption, even from the best IC fabrication company, TSMC on Earth. Right? What kind of assumption? The source and the drain, they are symmetrical. Their properties are exactly the same during your simulation, but for fabrication, sorry, they are not the same. Okay? You have more stack diffusion here, less diffusion there. Or you will face a lot of mismatch after fabrication, even for a single device, a single transistor. Oh. What you can do? What you need to do during layout, especially for analog IC designer. For critical devices, no. More specifically, for critical devices, for critical transistors of your analog circuit. I'm not talking about everybody. Forget about digital ones. They are very close to ideal. I don't care. They don't care. Okay? But for us, you don't need to take a good care of everybody. No. Only for your critical devices, your critical transistors. Then you need to pay attention to this. Their source and drain are not exactly the same during fabrication, right? But for your simulations, presim to post-sim, all of them are supposed to be exactly the same. Okay? Oh, so after fabrication, you will get a lot of mismatch. Just like this. Okay? What is the way to deal with this? You need to turn it over. Source drain, right? Then drain source. Got it? You need to have source, drain, source. And since, even for the same transistor, you can at least cut yourself into 50%, 250%, right? So, drain and source and drain. This is my own source, you can overlap it. Our source, drain source, you can overlap your drains as you like. That is the way we call stacked layout to deal with such kind of tilt waver. It must be. More exactly for your critical devices. Alright? And then we go for real construction, real fabrication. In the past, humankind only know how to fabricate all P MOSes or all M MOSes. But how to fabricate P and N on the same wafer? Oh, it is a big issue. Humankind spent, to my memory, 20 years to find the secret. But how to make it? Very simple. Yeah, on P minus subtract, you can fabricate your NMOS directly. Okay? But how about PMOS? No, PPP. We only have enhancement type for major circuit. Okay? So you need angle, then you can fabricate your PMOS. For such kind of fabrication secret, humankind wasted 20 years to make it. Okay? It is a very simple idea, but for fabrication, it's really hard. Yeah, anyway, we have N well or P well. Sometimes we have both, especially for SOI. Silicon over insulator, silicon on insulator. Okay? Oh, IBM from the beginning was the best for SOI. TSMC and UMC for mainstream fabrication, they don't use SOI. Okay? They use bulk process. So what is the difference? Anyhow, for SOI, all the devices are insulated from the substrate. So they can get an idea, better performance than bulk process. Just I mentioned, your NMOS can be fabricated directly inside P substrate. That is called bulk. Bulk, sometimes it's mentioned about your body. Okay, blah. So you have very strong interference between your substrate, between your bulk and your device. So in theory, bulk process gets a little bit worse performance than SOI. However, nothing is free. You need to pay extra process for SOI, right? It means what? It means it's more expensive and it's harder to develop. So for our two-dimensional MOSFETs, for TSMC, UMC, they only focus on this. They don't touch. Even though TSMC provides some kind of SOI fabrication services, but it never be the mainstream. It never be for mainstream market. Okay? Then let's go. Oh, this is, okay. Sorry. I had even better plot for you. This is the bulk we have, and that is the bulk for your MOS, for your PMOS. Anyhow. Okay. That is some kind of detail view for M-well process. We have M-well process, that is the mainstream for TSMC and UMC.